In a historic moment, astronomers announced today that they have confirmed century-old predictions about black holes from Albert Einstein and Stephen Hawking by studying the details of a black hole collision. To understand why this discovery is such a big deal, let's rewind over 100 years to the birth of the ideas that were just tested. Back then, both Einstein and Hawking were busy trying to understand the bizarre rules of gravity. You probably already know Einstein for his famous equation E equals mc, which shows that energy and mass are interchangeable. But his biggest contribution to our understanding of the universe was his theory of general relativity, which says that gravity isn't a force, but instead is a curving of spacetime caused by mass. Hawking, on the other hand, wanted to understand how quantum mechanics and general relativity might fit together. His most famous achievement was identifying what we now call Hawking radiation, the idea that black holes aren't entirely black and instead emit a thermal glow due to quantum effects. Now, both of these guys came up with some wild ideas that sounded pretty crazy at the time. But that's beside the point. Today, both theories are cornerstones of modern physics, but at the time, nobody thought that we would ever be able to actually test them, especially not with black holes. Black holes are notoriously difficult to detect because they don't interact with anything except through their gravity. So unless you happen to fall in one, you won't have any direct evidence that it exists. But Einstein and Hawking came up with two ideas about black holes that seemed testable in principle. At least, Einstein proposed that all black holes should be simple, pure examples of gravity whose properties could be completely described by just two parameters: their mass and their spin rate. Hawking, meanwhile, argued that the size of a black hole's surface area could never decrease. In other words, after two black holes merge, the surface area of the resulting black hole should be greater than or equal to the sum of the original black holes. Unfortunately, we couldn't test either of these ideas until we found a way to detect gravitational waves, ripples in spacetime, that are produced by accelerating masses. Like a stone dropped into a pond, gravitational waves spread outward from their source, carrying information about where they came from. Unfortunately, though, because they are so weak, they are nearly impossible to detect. That's why it took until 2015 for LIGO to make its first detection. Since then, LIGO, along with its European counterpart Virgo, have detected hundreds of gravitational wave signals produced by merging black holes. What makes GW 150,114 special is that the signal was incredibly clean, allowing researchers to look for subtle features. One of those features is a ring down, a brief burst of gravitational waves that is produced by the final black hole after the merger. Think of it like the last note of a song that lingers after the music stops. Just as different musical notes have different frequencies, the ring down of a black hole has a unique frequency that depends on the properties of the final black hole. When you hear a note, you can tell something about the thing that produced it. A higher pitch means a tighter string or a stiffer membrane. In the same way, the pitch of the ring down tells us something about the black hole. And importantly, it should depend only on the black hole's mass and spin rate, just like Einstein proposed. What's more, the ring down should be very simple, consisting of only one main frequency and a few harmonics, like the overtones of a guitar string. If there are any other frequencies present, that means the black hole is more complicated than Einstein's theory predicts. Another interesting thing about the ring down is that it should reflect the surface area of the black hole, just like Hawking predicted. The larger the black hole, the larger the surface area and the longer the ring down should last. So how did GW 150,114 check these predictions? Well, the team used machine learning algorithms to filter out noise and isolate the signal from the black hole merger. Then they looked at the resulting waveform to see what information it could tell us about the black hole. First, they focused on the first 10 milliseconds of the signal, which corresponds to the early stages of the merger. During this time, the black holes are still far apart and their gravitational waves travel essentially as separate signals. By comparing the two signals, the researchers were able to determine their masses and spin rates. They found that both black holes were roughly 35 times heavier than the Sun and were spinning relatively slowly. They then looked at the end of the signal, which corresponds to the final black hole as it settles down. They found that the signal lasted for about 7 milliseconds, which is longer than expected based on the mass of the final black hole. This suggests that the black hole may have been spinning faster than they can currently measure, which would decrease the total energy and thus increase the size of the black hole. But either way, it fits nicely with Hawking's prediction that the surface area of the black hole will be larger than or equal to the sum of the original ones. Finally, the researchers looked at the frequencies present in the signal. They found that the signal consisted of a fundamental frequency and an overtone. Just like Einstein predicted, there was one slight discrepancy though. The overtone was slightly closer in frequency to the fundamental one than expected. This difference could be due to a variety of factors, such as the presence of gas or the fact that the black holes may not have been perfectly circular. However, the researchers are still able to place 90% confidence limits on the mass and spin rate of the black hole, and their best estimate for the spin rate agrees with Einstein's prediction that the final black hole should be as simple as possible. It's not quite as simple as a mathematical equation, but it's close. After all, the researchers had to make some assumptions about things like the gas around the black holes and the shape of the orbit. Still, the researchers are cautiously optimistic that they have confirmed Einstein's prediction. "I think the confirmation of the no-hair theorem is super exciting," said lead author Maximiliano Isi, an assistant professor of astronomy at Columbia University and an astrophysicist at the Flatiron Institute's Center for Computational Astrophysics in New York City. "Everything there is to know about a black hole should come from its mass and its rotation. We see that in this case that description is good enough. Yes, there are corrections, but they are really small. Indeed, while the results are still preliminary, other experts agree that the data are consistent with Einstein's predictions. For me, this result is almost as good as one can hope for," said Lior Baruch, a professor of mathematical physics at the University of Southampton in England. "It is incredible to think that this kind of test is now possible. Even 10 years ago, it would have been inconceivable. Even so, the team acknowledges that more work remains to be done. For example, future observations by LIGO will allow them to improve their measurement of the black hole's spin rate and search for other potential sources of error. But even if the results hold up, it is not clear whether this will help solve the larger problem of reconciling general relativity and quantum mechanics. Some physicists argue that black holes can't be described by a simple equation because their quantum properties introduce an inherent complexity. Others point out that the necessary mathematics hasn't been developed to describe what a quantum black hole would look like. Still, the study represents a major milestone in our understanding of black holes and gravitational waves. As Emanuele Berti, a professor of physics and astronomy at Johns Hopkins University puts it, "We are entering the era of gravitational wave astronomy." This article was originally published on the website of Scientific American, a media partner of Seeker.